good morning all. Welcome back to Digital IC Applications class. In the last session, we have discussed the introduction to the CMOS logic circuits. So in the introduction to the CMOS logic circuits, we discussed what is a logic family, what is the significance of logic families, and the classification of logic families. And the important is the characteristics of logic families with respect to the digital ICs. So in this today's session, we will discuss the CMOS logic circuits. So these are the contents of the session, today's session. So we will start with the most important learning yesterday. So what we did learn in the previous lecture, and then we will see in this session the CMOS logic levels, and the CMOS logic circuits, about the CMOS logic circuits. So in the previous lecture, in the previous class, so we started with the logic families. So what is a logic family here? A logic family is a group of compatible ICs with same logic levels and supply voltages, fabricated for performing various logic functions, is referred to as a logic family. Or logic family is a collection of different ICs that have the similar characteristics, is referred as a logic family. So in a particular logic family will have the similar input and output conditions, and it will perform the different functions. And every logic family has a circuit configuration used to produce the digital ICs. So in every logic family, we use a basic circuit approach, and with that basic approach circuit, we will implement the different logic functions to that particular logic family, to particular logic. And the next is the significance of logic families. We have seen significance of the logic families. So why these logic families are important here? So the first one is simplicity in the design. So as the digital IC is fabricated using the basic electronic components such as diodes, transistors, resistors, and capacitors. So here the design is very simple, simplicity in the design. And second one, the members with similar electrical characteristics. So the other digital ICs in that logic family will have the similar electrical characteristics as they are approaching or as they are implementing with a basic circuit configuration, and reduces the complexity in the design. So since it is in digital integrated circuit, so it reduces the complexity and provides the compatibility in the digital circuit here. And the last one, easily expand. So you can extend the circuit, so using this digital ICs. And the next one, we have seen the classification of logic families. The classification of logic families here. Logic families are mainly classified into three categories. So on the screen, you are seeing only the two types of logic families. So the bipolar logic family, unipolar logic family, and the third category is bi-CMOS logic family. And coming to the bipolar logic families, the basic building blocks of bipolar logic families are the transistors, diodes, and resistors. And there are two types of logic families. I mean the logics used in bipolar logic families. So one is saturated logic, second is non-saturated logic. So here these saturated bipolar logic transistors are driven into the saturation region, and the non-saturated bipolar logic transistors are kept in the active region here. So the saturated logic families, the output is driven either in the cutoff region or in the saturated region. So because it is a digital device, so it will switch between the two logic levels, logic 0 and logic 1. So in this saturated bipolar logic, the transistor output is driven either in the cutoff region or in the saturated region. And there are different types of saturated bipolar logic families: resistor transistor logic, direct coupled transistor logic, integrated injection logic, diode transistor logic, high threshold logic, transistor logic. So out of all these saturated bipolar logic family, so the most widely used is TTL transistor logic. And the RTL logic and DCTL and the diode transistor logic or direct coupled transistor logic, all these logic families are obsoleted logic families. So presently they were not being in use. So in the saturated bipolar logic, the TTL is most widely used bipolar logic family. And coming to the non-saturated bipolar logic family, again it is of two types: Schottky transistor logic and the emitter coupled logic, ECL. In this saturated logic family, the output of the transistor, it is driven either in the cutoff region or in the non-saturated region. The non-saturated region is the active region of the transistor. So there is a difference between the saturated and non-saturated. Saturated or operated between the cutoff region and the saturation, either cutoff or saturated, 1 and 0. In non-saturated, the transistor will be operating in the cutoff region and in the active region. And as the non-saturated logic families are operating in the active region, so the non-saturated logic families are faster than the saturated, since the saturated devices are operated in the saturation region of the transistor. So that is about the bipolar logic family. And coming to the unipolar logic family. So in these unipolar logic families, the metal oxide semiconductor MOS devices will be used. So here again it is three types in unipolar logic family: the pMOS, n-MOS, the pMOS logic family, n-MOS logic family, and third one is the combination of the n-MOS and pMOS. So that is the complementary MOS logic. So in n-MOS transistors, we use the n-channel MOSFETs, and in pMOS transistors, we will use the pMOS transistors, and in CMOS, so it is, as I said, it is the combination of the n-MOS and pMOS. So that is the both n-MOS and pMOS transistors are used in the CMOS logic. And the third one is the bi-CMOS logic family. The third category of logic family is bipolar CMOS logic family. So in this bipolar CMOS logic, both the BJT and the CMOS are used. And here the bipolar logic family will be preferred to use at the output stage of the logic circuit, and the CMOS transistor will be used and it will be preferred at the input stage of the logic circuit, and even the logic function will also implemented with the using the CMOS circuit in the bi-CMOS logic families. So this is about the logic families of, this is the classification of logic families, so that we have seen in the previous lecture. And the important one we discussed in the last class is the characteristics of the digital IC. It is the characteristics of digital IC. So there are different parameters will be evaluated for comparison of the digital families, digital logic families. So they are, if one of the characteristic of the parameter is propagation delay. So what is a propagation delay? So it just the average delay time for a signal to propagate from input to output. And here the operation of the integrated circuit, the speed of operation of the integrated circuit is specified in terms of the propagation delay. So, so that's why here the propagation delay, it is recommended that it must be low here, and it is also advantageous that if the propagation delay of the circuit is low, so the speed of the digital IC is high. The speed of the digital IC, if the propagation delay of the circuit is low, the speed of the digital device is more here, and it is measured in nanoseconds. So simply the propagation delay is the average delay time for the signal to propagate from the inputs to outputs. And second characteristic is power dissipation. The power dissipation is specified in terms of the power consumption for the gate. It is specified in terms of the power consumption for the gate. Power consumption for the gate. And so usually in integrated circuits, so the power dissipation is specified in terms of the heat produced by the IC. The amount of heat dissipated is the power dissipation. And the power dissipation will be measured. It is measured in milliwatts. It is measured in the milliwatts, and it is also advantageous that the power dissipation should also be less here. The power dissipation should also be less. And third parameter is figure of merit. The figure of merit is the product of the propagation delay and the power. The propagation delay in turn, it refers the speed of operation. So therefore, on the other hand, the figure of merit is the product of the propagation delay and the power dissipation. So the units for this figure of merit, it is measured in picojoules. And here the figure of merit should be as low as possible. And the next characteristic is fan out. The next characteristic is fan out. So here the fan out is the number of loads that the output of gate can drive here. So without dropping the output voltage, the maximum number of gates that can be driven by the output of the gate here. So example, so take a NOT gate, and the first stage of NOT gate is capable of driving the 4 other NOT gates here. So the output of the NOT gate is capable of driving the other 4 NOT gates. So in this case, the fan out of this NOT gate is 4 here. And then the fan in. So the fan in is the maximum number of inputs that can be applied to the logic gate. The maximum input that can be connected to that logic gate. So example, so take an AND gate. So in this figure, the AND gate consists 4 inputs. So the maximum input that can be handled by this gate is 4. Therefore, the fan in is 4 here. And the another characteristic is, next one is noise immunity. Next one is noise immunity. So the noise immunity is the ability of the logic circuit to tolerate the noise voltage. So that is the maximum noise that a circuit can withstand without changing the output here. So without drop of the output, the maximum voltage or the maximum noise levels that can be accepted by the logic gate is noise immunity. It is noise immunity. And then the noise margin, it is the quantity measure of the noise immunity. The noise margin is the measure of the noise immunity. So that is, it is the limit of noise voltage that can be present without disturbing the proper operation of the circuit here. So these are the important generalized characteristic of an IC with respect to a logic family. So we have seen the propagation delay, power dissipation, figure of merit, fan in, fan out, and noise immunity. And there are other characteristics are also there. So we will discuss at the time of the CMOS characteristics in detail. So these are the characteristics that we have seen in our previous lecture. And now in today's lecture, so we will discuss about the CMOS logic. CMOS logic. So the CMOS logic is basically it is the combination of nMOS and pMOS transistor. As I said that it is the combination of nMOS and pMOS. And in this CMOS logic, the basic building blocks in the CMOS logic are the MOS transistors. So the CMOS logic gates can be built using the MOS transistors here. So therefore, before we going into the MOS transistors and before we step into the CMOS logic circuits, so we will see the CMOS logic levels. What are the CMOS logic levels? What are the CMOS logic levels? In any logic circuit, there is a range of voltages that is represented as a logic 0. So that can be interpreted to a logic 0, and another range of voltages, which are the non-overlapping range of voltages. So that is used to represent the logic 1. So since it is a digital device, as it is a digital device, it accepts only the logic 1 and logic 0. It responds to only the digital numbers 0 and 1. So we will have for digital circuits, we will have only two switching states, logic 0 and logic 1. The information maybe varies between the 0 and 1 only. So for not only to a CMOS logic, in any logic circuit, there is a range of voltages that is interpreted as a logic 0 and another range of voltages interpreted as the logic 1. So for instance, take a CMOS, a 5 volts, take the logic levels of a CMOS, which is operated from the 5 volts power supply. So the maximum operating voltage of CMOS is 5 volts here. Take an example. So now in this 5 volts of the CMOS, 5 volts operating voltage of CMOS, the logic 0 is interpreted between the voltages 0 and 1.5. So any voltage in between the 0 and 1.5 can be interpreted as a logic 0, and any voltage between the 3.5 volts to the 5 volts, it is interpreted to the logic 1 here. So 0 to 1.5 volts is representing as a logic 0, and 3.5 to 5 volts is representing as the logic 1. So now what about the intermediate range of voltages? That is the 1.5 to 3.5 volt. So when the given input lies between the 1.5 volts to 3.5 volts, it is an undefined logic level. So there is an uncertainty, and the circuit cannot define whether it is a logic 0 or logic 1, but it will give an output maybe set to a logic 0 or maybe set to a logic 1. So simply the CMOS logics, so any logic or any logic circuit you take, or in CMOS logics, there is a range of voltages that is interpreted as a logic 0, and the another non-overlapping range of voltages that is interpreted as a logic 1. And the voltages other than these two ranges will be defined as undefined logic level. It is defined as undefined logic level. Then we will discuss about the MOS transistor here. As I said that the MOS transistor is the building block, the basic building block for the CMOS logic. And as we all know, what is a MOS transistor? Metal oxide semiconductor transistor. It is a 3-terminal device. It is a 3-terminal semiconductor device that act as a voltage variable resistor or a voltage control resistor. So which means when an input voltage applied to one terminal, it controls the resistance between the remaining two terminals. So if you see in the diagram, so it's showing the 3 terminals of the MOS transistor, 1, 2, 3. And when you apply an input voltage V in, at the input terminal 2, and the amount of input voltage will controls the resistance between the other two ends, that is between the 1 and 3. So here the MOS transistor can be used as a voltage control resistor or a voltage variable resistor. As you vary the voltage, so it will controls or it will change the resistance between the two ends here. Between the two ends here. So next, we will see the types of MOSFETs, MOS transistors. So mainly there are two types of MOSFETs, n-MOSFET and p-MOSFET. N-channel MOSFET, p-channel MOSFET transistors. So n-MOS transistors and p-MOS transistors. So here you can see the logic, here you can see the schematic representation of the n-MOS transistor and p-MOS transistor. So it has three terminals, drain, source and gate, and you are applying the voltage between, if you apply the voltage between the gate and source, it controls the resistance between the drain and source, or the amount of charge carriers that flows between the drain and source can be controlled. And this figure B is the pMOS transistor. Again here also, if you see, the voltage is applied between the gate and source, but the difference between this n-MOS transistor and p-MOS transistors with respect to the applied voltages here, with respect to the applied voltages. The n-channel MOS transistors operated with the positive gate voltages, whereas the p-MOS transistors operated with the negative voltages here, negative voltages. So positive gate voltages and negative gate voltages. So as far as concern the n-MOS transistor, so when a positive gate voltage is applied, the n-MOS transistor will be in on state. And when you apply the 0 volts to the n-MOS transistor, it will be in the off state here. But if you see for the pMOS, it is a contrast to the nMOS transistor. So in p-channel MOS transistor, when you apply the negative gate voltages, the pMOS is in on state, and for positive voltages, the pMOS is in off state here. So here the nMOS and pMOS, they are offering the quite opposite electrical characteristics here. So in digital applications, if you see, so let the input is Vin, and for Vin, if you apply the voltage of VDD, where the VDD is a positive voltage, so when you apply the Vin is VDD, so the nMOS transistor is in on. For Vin is 0, the nMOS transistor is off. So when the transistor is on, it offers the low resistance. When transistor off, it offers the high resistance. So similarly, in pMOS also, when Vin equal to 0, the pMOS is in on state. So for negative voltages and for 0 voltages, the pMOS transistor offers the low on resistance. For positive voltages, the pMOS transistor offers the high resistance. High resistance here. So simply to conclude this slide, so the nMOS transistor will be on for logic 1, I mean for VDD equal to logic 1 or 5 volts. For Vin equal to 0 or logic 0, the nMOS is off. For pMOS, the Vin is 0 or logic 0. For 0 volts or logic 0, if you apply pMOS, the pMOS is in on state. And if the Vin is positive voltage, say the VDD, so the pMOS is in off state here. So here the alternate way of symbol representation, the schematic representation for the pMOS transistor and nMOS transistor. In the previous, if you see, so for nMOS transistor, the arrowhead is pointing out towards the source, and for the pMOS, it is pointing out towards the gate. So that will be also represented in different ways. So here you can see the alternate schematic representation for the pMOS and nMOS. So for the nMOS and pMOS, if you observe here, the pMOS has a bubble on the gate input. Why it has a bubble on the gate input? Because the characteristics of the pMOS transistor is opposite to the nMOS transistor. So for nMOS transistor, if you apply the 5 volts, it is on. If you apply 0, it is off. But whereas the pMOS, if you apply 0 volts, the pMOS is on. If you apply the 5 volts, the pMOS is off. So which means it is opposite to the nMOS transistor. So that's why to differentiate the pMOS and nMOS transistors, so they have kept a bubble on the gate input here. So it is negative gate voltage for the nMOS transistors, and for the pMOS is positive gate voltages. Sorry. For nMOS, it is positive gate voltages, and for the pMOS, it is negative gate voltages here, right? So till now we discussed what are the basic building blocks of CMOS logic. The CMOS logic, in a CMOS logic, the basic buildings are the MOS transistors. And we discussed CMOS logic levels. So what are the CMOS logic levels? In a CMOS logic circuit, there is a range of voltages that is interpreted as a logic 0, and the another range of voltages that is represented as the logic 1. And then we discussed the MOS transistor types, nMOS and pMOS. So now coming to the next one, CMOS inverter. So here the CMOS inverter is the basic building circuit for the for to implement or for to build the remaining CMOS circuits. So it is the basic building circuit in the CMOS logic, CMOS inverter. And the CMOS inverter is the combination of the nMOS and pMOS transistor. So the nMOS transistor and pMOS transistors are used together in a complementary way to form the CMOS logic. So that is the CMOS and that is the nMOS and pMOS transistors are connected. So they are in CMOS inverter, we use the nMOS and pMOS transistors. So here you can see the circuit diagram of CMOS inverter. So where we are using one pMOS transistor and one nMOS transistor. The pMOS transistor is connected to the power supply VDD. That is, the drain of the pMOS is connected to the VDD, and the source of the P channel is connected to the drain of the N channel, and the N channel source is connected to the ground here. So simply here the pMOS transistor is connected to the power supply VDD, and the N channel MOS transistor is connected to the ground here. It is connected to the ground, and the gate input of the two transistors are connected together, and a single output is applied to the gates of the two transistors here. So depending on the input at the gate and the P channel and N transistors are operated, and accordingly that, so this CMOS circuit will produce an output. But here if you see, there are two terms here, pull-up network and pull-down network. What is a pull-up network and what is pull-down network? Pull-up network. So this pull-up network, it is always used to drive the output to the logic 1. It is used to drive the output to the logic 1, where the pull-down network, it is always used to drive the output to the logic 0. Logic 0. So that's why here the P channel transistor, it is also called as the pull-up network, and the N channel transistor is it is also called as the pull-down network. So why the P channel is a pull-up network? Because the P channel, which is connected to the VDD, is always try to force the, or it is always try to drive the output to the logic 1 value, high state, where the N channel is always try to force or drive the output to the logic 0. So remember that the pMOS transistor is a pull-up network and the nMOS transistor is a pull-down network. So furtherly, we use these terms for the describing the operation of the circuits: pull-up network and pull-down network. And then coming to the functional behavior of the CMOS inverter. So here again you can see the circuit diagram of a CMOS inverter and the functional behavior and the logic symbol. And basically, and as we all know, the functionality of the an inverter gate or an inverter circuit. So that is, when you apply an input, when you apply the input as logic 0, it produces the complement of the input, that is 1. And when you apply the 1, so it produces the output as the complement of the input, that is 0. So for 0, it produces 1. For 1, it gives 0. So now let's see the operation of the CMOS inverter. And the operation of the CMOS inverter is described with the help of the switching model. So where this switching model will help us to describe the behavior of the circuit, and we can also easily understand the operation of the CMOS inverter. So let's see the switching model of CMOS inverter. So now, as it is a one terminal gate, so as it is a one input terminal to this CMOS inverter, so the probability of having inputs is 2, either logic 1 or logic 0. That is, logic 1 either 5 volts, logic 0 is 0 volts. So now take the condition input is logic 1. So when the logic 1 is applied, so for logic 1, the nMOS transistor is in on state. For the pMOS transistor is in off state here. So when the input is 1, the transistor Q2 is an nMOS which is in on state, and the transistor Q1 is a pMOS which is in off state here. So the Q2 nMOS on, Q1 pMOS off. So since the Q1 is in off state, so it just simply representing as an open circuit, therefore the VDD, it cannot reach us to the output. But on the other hand, if you see, the Q2 transistor is on, the nMOS transistor is on, and so when it is on state, so it just establishing a short circuit, and therefore it is just simply grounded here. And now if you see the voltage at any point at the output circuit, at the Q2 or at the output, these two are maintaining at the same potential value, that is 0 volts. So for a logic 1, if we apply this circuit producing the logic 0, so which is the correct operation for a CMOS inverter. So if you apply 1, the output is 0. And next, take the second condition, input is 0. So when the input is 0, when the input is 0 applied, so now for logic 0, the pMOS transistor Q1 is on, the nMOS transistor Q2 is off. So now the nMOS transistor is open circuited and the pMOS transistor is closed circuit. That is, the pull up network is on and the pull down network is off. So since the Q1, the pull up network is on, so the VDD is directly connected to the output. So therefore, the output of the circuit is 1 when we apply the logic 0. So this is the operation of the CMOS inverter. So for concluding for this session, so we need to remember the electrical characteristics of the nMOS and pMOS. What are the electrical characteristics of the nMOS and pMOS? When you apply the logic 1 to an nMOS, it is in on state. When you apply logic 0, the nMOS transistor is off. And for pMOS, when you apply the logic 1, the pMOS is off, and when you apply the logic 0, the pMOS is on. So which means the N transistor and P transistors are giving us the complementary characteristics here. So using these two devices, so here the CMOS inverter circuit is realized here. So for today's session, we will stop here, and so we will continue the CMOS circuits in the next lecture hour. So I think you understand the concepts of this CMOS inverter. Okay, thank you all.